dear committee chair, committee members, opponents, dear supervisors, dear friends and colleagues, good afternoon. I am very happy to have you here today. Herewith, I would like to present to you a summary of my study and conclusions of my thesis. We started study on properties of solution for some kinds of fractal and differential equations. This presentation is structured as follows. We begin with a brief introduction, and then we move on to the main result, and finally we get some future work. So, begin with the introduction. Fractional calculus becomes significant for application for both the ordinary and partial differential equation with fractional order have been used recently in modeling of many physical phenomena and chemical process and engineering and technology. Numerous new definitions of fractional derivative and fractional integral have been introduced recently. In recent years, many academics have investigated the properties of solution for different kinds of linear and non-linear fractional differential equation with initial condition or boundary condition or non-local conditions, etc., or a combination of these conditions. So here in this presentation, I'm going to show you the following kinds of fractional differential equations that we have been studying and obtaining existing results. We first study the non-local Hilbert fraction evaluation problem shown by system 1, and the second one is the nonlinear multi-term psi-carbon fractional differential equation with infinite delay. The third one is nonlinear fractional differential equations given by system 3, and the fourth one is subdivision system with Hilbert fractional derivative. So let us move to the main result. The first study is existence of mild solution for non-local evaluation equation with Hilbert derivative. We study the non-local problem 5, where the derivative is given in the sense of Hilbert fractional derivative. A is an infinitesimal generator of strongly semi-group of bounded linear operator in a Banach space. F is a nonlinear term, which is assumed to be continuous here, and this integral is Riemann-Leibel fractional integral. And G is a non-local item, which is also assumed to be continuous here. So the definition of Hilbert fractional derivative and Riemann-Leibel fractional integral as given by equation 6 and equation 7. So we have some assumptions that we are using in the proof of our conclusion. The first assumption is the assumption HQ. We assume that the operator Q2 is a compact operator for t greater than 0. And also we assume the assumption HF for t in J. We prove that the function f is a continuous function and also is strongly measurable for t in J and here. And the inequality S and f is given by the inequality S in terms of the function f psi and the constant L. The third assumption is the assumption HG. We assume that the non-local item here is a continuous function. We satisfy the following assumption. So in this definition, the Maya solution of the non-local problem 5 is given by equation 9, where V belongs to that Banach space, and S and T are given as below here. So in this theorem, we assume the assumption HQ and HF and HG satisfied together with the condition 10, then the non-local problem has at least one Maya solution on A dash. So we use approximate technique and we introduce the following approximate problem given by system 11, where Q is the compact semi-group. So we are using the here square fixed point theory. We introduce operator G and prove that G has a fixed point by proving that G is completely continuous. So in this lemma, if all the assumptions of theorem 4 are satisfied, then the local problem has at least one Maya solution Bn. This is the approximate problem that we have introduced in the past slide. So to transform the problem to a fixed point theory, we define the operator Gn given by equation 12. here this just for simplicity of calculation. Equation 13. So we prove that Gn has a fixed point in the following step. We first prove that the operator Gn maps the set PR dash n to PR dash, and then we prove the map Gn is a continuous from PR dash. Also, we prove that Gn PR dash is equicontinuous, and also we prove that there is arbitrary closed subset which are relatively compact close to the set ZT, then ZT itself is relatively compact. Then we get the minus solution of the approximate problem. So we reconstruct the solution set W as given here. If we prove that W is pre-compact in this Banach space, then the problem, the first problem that we have seen there has a minus solution. So to prove that W is pre-compact, we prove that for T in J dash, WT is relatively compact and W is equicontinuous. And so in this lemma, we prove that W is relatively compact in this Banach space. Then the minus solution of the approximate problem, we can, after we prove that W is a pre-compact, then we can take the limit for n equal plus infinity. Then we get equation 15. The equation 15 is the minus solution of the non-local problem. So we sum up that we have derivative. We study the system 34, where also the derivative given here in the sense of Hilbert fractional derivative, and the operator delta y is given by 35, where the function p and q and r are assumed here are continuous in the closure of the domain omega t. Also, we have some restriction. We restrict that p is greater than 0 and the function r is less than 0. So the definition, so for the function belongs to the space SC gamma, we can say that the Hilbert fractional derivative of this function is just equal to Riemann-Leibel fractional, is equal to Riemann-Leibel fractional derivative minus this term. Just we use this in the following. So we prove the experiment principle that for any function belongs to SC gamma until it is maximum at a point which is 0, then the inequality 37 is false. So here we prove the maximum principle for the function. If we prove that yt is a solution of the given problem, if yt belongs to the space SC gamma, then and also with the initial state is less than 0, and then inequality 38 false, then we can say that the maximum of the solution at the closure is less than or equal to the maximum at the boundary. So the minimum principle is just opposite of the past result. So again here, if the solution belongs to the space SC gamma and the initial state is greater than 0 and inequality 14 whole, then the minimum of the solution at the boundary is greater than or equal to the minimum at the minimum at the closure is greater than or equal to the minimum at the boundary. So we can use this result to get some error information about the solution. So for the nonlinear term, if the nonlinear term is greater than or less than or equal 0, and the initial state is less than or equal 0, for the solution belong to SC gamma, then we can guess that the solution is less than or equal 0. This means that the given problem has no positive solution in the space SC gamma. Theorem 23 is just opposite of that. If we assume that the nonlinear term is greater than or equal 0, and the initial state is greater than 0, then we can say that the solution is greater than or equal 0, meaning that the given problem has no negative solution in the space SC gamma. So we conclude that we prove the experiment principle, and also we have tried and proved the maximum principle and minimum principle, and we obtain error information about the solution of the given problem. So the study 4, we study the following subdivision system with Hilbert fractional derivative. Here, the initial state we assume here is unknown, and this system is, we just have this information about the system. We have just, the measurement is given by equation 45, where C here, C is a linear operator, which is called the observation operator with a dense domain. DC belongs to subset or equal the helper space L2 omega. L2 omega, we call it the state space here. So since C is an admissible operator, as we have remarked in our thesis, then we can write the measurement by equation 46, where K is called the fractional operator. So to obtain the adjoint of operator K, we have two cases. C is bounded. We can define here so-called zonal sensor. C is unbounded. We can define so-called point-wise sensor. So we characterize the problem by the following. We just want to see that the system is observable in a sub-region. If we notice here, this is L2 small omega. Sorry. We assume the set E given by this. If we assume that the state of its space belongs to the subregion of L2 omega, which is a subregion of the main space, then we assume the initial state has two options. The option one, B0, we call it B01, when B0 lies in the set E. We call it B02. This is in the L2 omega removing E. This is the undesired initial state. The idea that we want to use the uniqueness property to reconstruct the initial state in a certain region, this one. So we have the following theorem. The following assertions are equivalent if we call that the system 44 with the output function is exactly E observable in the subregion omega. This means that the image of PWK star, PW is call it a restriction operator, which is mapped from the state space to the subregion, and K star is the dual of K intersecting with the set E is not an empty set. So now we use the Hilbert's uniqueness method. The Hilbert's uniqueness method, we set the space E as given by 48. So as we have seen earlier, we have two options for C. C is bounded, C is unbounded. If C is unbounded, we have so-called point-wise sensor. Then the measurement can be written in terms of equation 49. So the idea also here, the Hilbert uniqueness method, there are some steps that we are following until we prove that the system is whether it's observable or unobservable in the given sub-region. So we introduce the system 50 here. Then we use a reflection operator to reflect the past system. You can notice here we have this called reflection operator. This system 51 is controlled by the past state of the past system, as you can see here. This is the control here. So according to the Hilbert uniqueness method, we define the operator lambda from the space mapping G to G star, where G star is the duality of G. Then we reconstruct the equation 52. If we prove that lambda is isomorphic, then we can say that the solution here is a unique, which coincides with the desired space. So we introduce the system 53. If we choose the initial state of psi 0, such that phi 0 is equal to psi 0, then we can also introduce the equation for 54, and we solve 54, which also is coincide with the previous one, this one, 52. Then in this theorem, the given system with the given measurement is exactly E observable in the subregion omega if equation 52 has a unique solution. which is the initial state, the psi 0, belong to G. That coincides with the desired desired state space, which is B01, between two functions, as we introduce E, in the subregion small omega, which is this is a unique solution that we want to reconstruct. So when C is bounded, then we have so-called Dun or Dunal sensor. The meaning is the same. Here, just since C is bounded, then we define the sensor in the term dH. Here, D belongs to the domain omega, and H belongs to the helper spec L2D, which is here is bounded. Then the measurement can be given by equation 55. All the steps is similar to that one. Once just C, we assume C here is bounded. Then we can conclude that we have investigated the given problem and developed approach based on the helper uniqueness method, and we reconstruct the initial state, and we obtain the desired state between the given profiles. So for future work, our study can be expanded to the following. We can study the regularity of the solution for non-local helper evaluation equations. Also, we can study the existence and higher Celan stability for multi-term K psi Caboto fraction derivative with infinite delay. Also, we can study the maximum principle for helper fraction integral differential equation, and we can also study the regular graph of the derivative for subdivision system with K psi helper fractional derivative. This talk is based on the following paper. I have some acknowledgements that I want to state. First of all, I would like to, I'm very grateful to my supervisor, Professor Lee, for giving me the first opportunity on my lifetime by being one of his students. I really appreciate that, and definitely this will improve my career in the future. And I have no words to express my gratitude to Professor Van for the good collaboration that we have had recently. And thanks also to Professor Dong. I also acknowledge the National Science Foundation of China for the generous funding that make this possible. And also I would like to acknowledge the staff of College of Overseas Education and the staff of College of Mathematical Science. And thanks to all my friends and colleagues for coming to attend this event. Really, this means a lot to me. Special thanks to my family members, my wife and my daughter. And thank you for listening.
那李老师，我们就提问环节。
你说算了。
好，下面呢，我们就进入到这个提问环节哈。各位专家、还有老师、同学，还有什么问题哈？下面问的时候，我觉得用中文或者英文都可以吧。或者是如果我们中文吧，用中文问了以后，年轻的可以他们帮着翻译一下。
他们学了1年中文。
啊，那就徐老师，你来，用中文也可以，英文也可以。对。
我没听得太那个清楚，就是他那个，就是他那个半裙它是紧的，对吧？你晓得那个，然后它实际上面那个，实际上相当于把颈巾放到那个半裙上面去，对不对？
肯定是一个颈子，这儿没有那儿有。
问题我也没有什么问题，这个东西做的我细的东西我也不懂，我只能看大概的东西。
你是专家。
没有。
这样其实，改变你来说，我说有你和合作的文章，你提个吧。
没有，主要把这个习性嘛。
对吧？
我们干嘛I have a question. In the definition of phi capital fractional, why you need the function phi is increasing function? Is there some good properties for this?
The function phi to be increasing function.
Yeah, why?
I think this from the definition. It's given in a definition. Maybe they restrict that phi to be increased function. According to the definition. So phi here in the definitions, phi to be increasing in the definition.
Yeah, I want to know why. Is there some good properties for this?
The good property, I guess, well, I have no idea about it. I just found it in this definition. I don't expect when phi is to be increasing, I don't know.
你刚才看到，我就想问一下。
I just asked you in chapter 5, you say the Hilbert Unix method approach. Can you explain this method?
Okay, the Hilbert Unix method is based on the uniqueness of the solution. So, if we prove that the solution is unique, we have some steps we are following. This method introduced by Professor called Leon. He used the property of the uniqueness to in fact, this problem is more practical in the practical field. There are many restrictions on this one.
叫解的区，就是控制函数的区。
The Hilbert Unix method guarantees that, for example, if this is a system, we can measure a system in a certain subregion. If we get the information of the system in this subregion, then we don't need to measure this big system. So this property is very useful to measure a big. For example, there is call it chemical reaction. Chemical reaction is very big. We can't measure everything in the system. So even if we study the theoretical part, but we have a little idea about what is going on. We just know that if we can measure the system in the subregion, then we can generalize the problem. That's why the problem is called enlarged observability.
I have a question.
Okay.
Which result or which character is the best one you think?
I think the best one is the maximum principle, because the maximum principle, to define the maximum principle in the Hilbert sense, it has no any study before this. And Hilbert fractional derivative has a combination of Riemann level fractional derivative and Caputo fractional derivative. So this result is generalized both of them, and I think it's a good one. On my opinion. Yes.
当时他针对的这个就是那个 principle 有一个理论，他要自己去证，所以他找不到现成的，自己去证一个。
它这个函数，看怎么它上面写的这个向量啊，不是一个函数啊，函数它怎么会大于等于零，小于等于零呢？原来是 r 到 r
R 应该是写 R。
对吧？我看它里面全是 r， 是吧？我当时还在疑惑，我说是不是每个分量都要证啊？
几个问题了？
4、5个。
你们翻译一下啊，就是我想问一下，你这个处理的是这个 Hilbert 的这个分数界导数，那么这个分数界导数的话，你这个是卡普特和黎曼吕尔型的推广， 你这个推广当然就是这个东西是它的推广，你做这个东西当然有意义。我是说从方法上来说的话，你把它统一起来处理的话，有什么就是说处理这个
小黄或者是跟你也给翻译一下。
黑尔夫的这个分数解导数，它有什么就是方法上有什么这个便利之处吗？就是说有什么优越性？就是你处理它的时候，统一起来处理，这两组统一起来处理，就是说能听懂。
Got it?
No, I lost.
Professor Ho asked, is there 我想要怎么翻译了？
你可以再说一下。
就是你的那个，就是他不是定义那个他处理的那个黑尔夫的那个分数解导数，这个分数解导数呢是黎曼刘维尔和卡普特型的这个推广，它既包含了黎曼刘维尔，也包含了这个卡普特的。那么这样子的话，就是你统一处理它，那么就是方法上有什么便利吗？就是说，当然推广肯定是有意义的，因为你一个包含两种，就是比起人家你单独处理黎曼刘维尔或者是卡普特，就这个意思。
处理这个，
对，统一起来是不是
有什么好处吗？
有什么好处？对。
说起来，首先这个它根据理论上是
有用的，
我问不出来这个问题，这个问题我不太好问。你说方法上有什么？
那我就是他处理的过程中，你比如说比起人家原来黎曼刘维尔的，有方法
可以给他翻译一下，问一下让他来回答。
对，
这个in this thesis you deal with the Hilbert fraction. It means you can in a unit way to deal with the capital fraction equation and the Riemann equation. So there is there something special or good method to prove in all things.
You know, the fractional derivative is developing very fast. The Hilbert fractional derivative, if we can say that here the division, for example. Yeah, the Hilbert fractional derivative. The Hilbert fractional derivative, there is another variable, k. If we say this cover. This variable makes this derivative special because there are some like practical problem has more than two variables or three variables. So the Hilbert derivative is assumed to be very good one because there is another. If you see capital Riemann, there is only one variable, but here we have another variable. As I say here in the conclusion, what I said here. There is another, for example, k f psi. So k f psi also is more advanced than f psi capital derivative. So if we expect Hilbert fractional derivative, there is another new definition. For example, k f psi Hilbert derivative. Where is it? I suggest here.
For example, in chapter 2, you prove the existence of Mark solutions. Is there any difference between Hilbert equation and the capital equation?
In the scope of my solution, I think there is no big difference because the difference is in the kernel. The Hilbert derivative, the kernel of Hilbert derivative is a little bit different from the kernel of Riemann or capital derivative.
But in your proof, what's the difference?
The difference is we just use the method, for example, approximate technique. We don't use the Lipschitz continuity, so this is makes this study different from the previous study.
This is one. Another maybe I think is the space. The space is
The space SE1. here in the space, yeah, this is space.
You can see G, the definition of G. G from C1 minus gamma to V.
Yeah. Here.
就是处理这种问题的时候，这个基本空间不太一样，它很多都是要加权的，因为它这个导数定律里面有两个参数。
对，它这是双参数的。
大家看还有什么问题？啊？对，对，啊。
Could you explain the definition of right function?
A red function.
Page 15. On page 15.
Page 15.
Okay.
就是来，你可能问的有个就是来自概率论里面，跟概率论有关。啊，它反应跟我去这个声音反应 right 反应这种就 right 就 right。
这是中文中译的名字。
好像没有。
你这是那个，这 right 请问一下 W right W 火。
这个 W 不发音的。
我知道。
后面 right。
The red function.
这个本来来源是跟概率的，跟概率的，它后面也有一些概率的，都往后跑。我们也看，I want you to
Theta. The best function for the the variable theta, if variable theta is greater than 0 and less than or equal 1, is a summation of, we assume this C, theta, we can take it T or anything. It's minus theta n minus 1 and over the n minus 1. This is gamma function 1 minus theta n from n1 to infinity. This is the statement. We are using this function here just to estimate the following integral. The use of this function is from 0 to infinity. In the infinity case, this is theta. Here, call it theta or anything. Yeah. Theta. So for theta from 0 to infinity, we just want to use this direct function that give us, estimate this, give us gamma over
你真正最有参考性的实际上
So in the case of the rate function from n to infinity, we use it here to get the the convergence of this integral to be like this one. So this is the use of the rate function here. This is
In my opinion, this function may be considered with the proper
probability function.
Where we use the Laplace transform to look for the solution for the equations. We maybe use this function.
Okay.
行，到时候答案再多写一点。
就到时候你让他再写一个，再写一个就是那个，他们有一个那个强可测，强可测的话和普通可测的这个，就是说如果定义不明显的话，让他举个例子说明一下。函数是强可测的，不是普通可测的。
其实我发现里面它这有个别类似于那种语法性的，虽然说
语法他们是说，但是语法的。
不，我是说什么？比如说刚才我就看到一个，类似一个引领器的。
他们的实践能力不强，但是语法可能不
啊，那英文是。
就是他这个第一篇文章我改死了，然后改了几十遍了，真改了几十遍，当时他还不在这儿，回国了。他那个微信是时通时不通。
你比如说这个引领的链接，像按我们经常说的，它是引领它什么什么，然后这个方式，是啊，这应该两个句子吧？应该是两个句子，就是他自己写了一下。
原来的话，他们市场就是
那应该是对啊，
行，我看着这大家已经也问了不少问题了啊。那这样，那我们就是是不是他们应该先回避一下？
对，要回避一下，然后这儿有票。
啊，有票，好的。
哎，那个藏书的时候，
we discuss, so just one minute.